And go. Hello and welcome back to Calculus 2. We are starting the infamous chapter on sequences and series. This is the first lecture on sequences. So we will talk about, in this part of Calculus 2, we'll talk about three different things now: sequences, series, and power series. So sequences will be covered in the first two sections. For the rest of the chapter 10, we will cover series, 10 tests. And then in the chapter 11, 4 sections on power series. So what is a sequence? Definition. Sequence is ordered list of numbers. So it's not a set. Sets don't have to be ordered, and sets don't have to be numbers. I can say set of students. That's all of you. Set of desks, set of trees. Sequence is the ordered list of numbers. So it is a set of numbers, but it's ordered. Now, ordering is done through natural numbers. Ordering is achieved through natural numbers, also known as counting numbers. Now, 0 doesn't really belong to this set. Sometimes we use it, sometimes we don't. Usually when you count, if I want to count how many students I have in this classroom, I'm not going to start with 0, 1, 2, 3, 4, 5. I'm just going to say 1, 2, 3, 4, 5. So natural and counting numbers start with 1. And that's that set capital N with 2 bars. You know how you have a capital R with 2 bars and that set of all real numbers? Well, that one has fractions and irrational and pi and all of the other numbers. Set of natural numbers only contains counting numbers: 1, 2, 3, 4, 5, 6. And ordering is clear because so that's the set of counting numbers. Now, I'm just going to say over here, we can use 0 if we want / need. So some problems will have 0, some problems will not have 0, depending on the situation. It will be clear what's going on. So ordering is achieved through natural numbers, counting numbers, and that's that. Now, notation. Sequence AN. AN is, we can start with A0 or A1 and just go in order all the way to infinity. Now, sequences can be finite, can be infinite. We'll get there. Now, you see the ordering 0, 1, 2, 3 for the first term, second term, third term, and so on, right? Guys, this is insanely important. If you're computer science, you need to understand all of this down to the goriest detail. That's your one-dimensional array, with the first value being 0 as a location, and the next one 1 if you use Java. So, there you go. So I can have a series of numbers, say, example, AN is equal to 1 half, 1, 1 half, 1 quarter, 1 over 8, 1 over 16, going on forever. It's a sequence separated by commas. It's a list of numbers. And if you carefully look at this, you have 1 as 1 over 1. You see that the denominator grows as the exponent of 2, right? So we can write this as an is equal to 1 over 2 to the n, where n starts at 0 and goes on forever. Try it. A to the 2 to the 0 is 1. 1 divided by 1 is 1. The next number is 1. 2 to the 1 is 2. You get your 1/2. The next number is 2. 2 squared is 4. You get your 1/4. And so on. So these numbers are carefully ordered through this set. So there is a formula, and then there is the set, the list of all numbers. Sometimes the formula is given to you, an, say 3n minus 1, and then you come up with the list. Starting at 0, starting at 1, it's specified. If it's not specified, you can start wherever you want. You will understand that we actually don't care what's happening at the beginning of the sequence. We care about what we call the tail end. So we'll talk about these things. So let's say you start at 1. So n equals 1 is the first one. So that's going to be 2. And then the next one, n is 2. So that's 5, because 2 times 3 is 6, minus 1 is 5. And then you'll have 8, and then 11, 14. So they increase by 3, going on to infinity. So sequence is not nothing scary and spooky. It is just a list of numbers, and then you look at that list of numbers and you try to find a pattern, try to find what the formula is. Now, some sequences are given as what we call recursion, where the new term in a sequence depends on the previous terms. You already know one of those sequences. It's mentioned in pretty much every math course, and a lot of artists use it, and so on. Does anyone know? The Fibonacci sequence, yes. So Fibonacci sequence has a pattern where you add 2 consecutive values to get the next one. So Fibonacci sequence, recursive sequences, use previous terms to make new terms. Fibonacci sequence is, you start with 1 and 1. And it was explained with the multiplication of rabbits. You start with 1 male and 1 female rabbit, right? So 1 plus 1 is 2. Pairs of rabbits. So 1 plus 1 is 2, and then 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. And you can continue that pattern indefinitely. Now, I would like to have a formula for this. If you are computer science guys, try to code pretty much everything we put in this class to practice. We can make a formula where, and you can do it 2 different ways, so I'll explain both. Look, you take a term, an. It could be A0, could be A1, could be A10. So you take one of the terms, and you add to it the next term. You see, that n can only be an integer. So if you took A5, then the next term must be A6. And Fibonacci, so 1, 2, 3, 4, 5, and 6. There they are. So this would be a 5, and this would be 8. That creates the next one in the line, which is n plus 2. So this is one of the ways to write Fibonacci sequence as the recursive formula, where the new term in the list depends on the previous terms on the list. Now, you can also, or you can say, if I want to get the an term, if this is something that, like if this is your target, then you will add previous two terms. These two formulas are the same. They're just shifted. You see, I can say, give me two consecutive numbers, and I'll give you the next number. So that formula in Fibonacci can be understood this way. Or you can ask me, how do I get a specific term? And I tell you over here, oh, this is supposed to be a plus here, guys. It's a plus. And I tell you on the right-hand side, add two previous terms. See, so if I'm looking for A8, right, if this is A8, I'm looking for the 8th term, then this would be A7 plus, and this is A6. Right? I think it's very straightforward of what's going on. Over here, I can say take A6, add to it A7, and you will get A8. Because if n is 6, then plus 1 would be 7, which is the next term, and then plus 1 would be A8, which is the next term, which you get when you add the previous two terms. So sequence is the ordered list of numbers for which you can have formula. And if that formula happens to rely on the previous terms, we call that formula recursive formula, meaning that you have to use previous terms to generate new terms. So this is technically a term generator, the formula. Now, for Fibonacci sequence, it's what you see. Now you can literally come up with anything you want, right? So you can say, for another example, for the recursion, say you have a formula 2an plus, I don't know, 2an plus 3a n plus 1 minus 6 is equal to an plus 2. If you have this, you also have to be given first two terms. So let's say a of 0 is 2, and a of 1 is, let's say, 4. So first two terms are given. Okay, so for n equal to 0, I have 2a0 plus 3a1 minus 6 is going to give me a2. So that's the first term. And because you have a0 and a1, you can calculate the value. So that's going to be 4. I mean, you have to calculate value. Plus 12 minus 6 is equal to 10. Now, we know that a2 is 10. Now, when n is equal to 1, you have 2a1 plus 3a2 minus 6 is equal to a3. Hey, you just calculated a2. You have a1, you calculated a2. Well, plug them in and come up with a3. So a1 is 4 times 2 is 8 plus 3 times 10 is 30 minus 6 get 32. So a3 is 32. And the last one I'm going to calculate because I'm bored now. N equals to 2 is 2a2 plus 3a3 minus 6 is equal to next term, which is after a3 is a4. Well, you have a3, that's 32. You have a2 is 10. So 20 plus 96 minus 6 is 110. So a4 is 110. Well, this already has 5 terms. So we can write a nice sequence: 2, 4, 10, 32, 110, 3 dots, meaning you can go to infinity if you want. Keep calculating a new term and a new term and a new term, and see how far you go. So that's the recursion. You have to have a formula that uses previous values. Now you have to have input given. Remember, in Fibonacci sequence, we said the first 2 terms are 1 and 1, and then that sets off the rest of the calculations, because you will always add 2 consecutive numbers to get the next one in the list. So that's our story of basic sequences, and now we're going to take a look at what the sequences actually do. See, a sequence can be finite and a sequence can be infinite. Finite sequences are not really important or fun because you just have a finite amount of numbers on a pile and there's nothing you can really do with that. We look at infinite sequences and call them sequences, are the ones that go to infinity. So sequence can be infinite. We use the limit test to check if the sequence converge or diverge. I'm aiming for you, so you better move. Well, you caught it. At least. Fine. Limit test. Limit test. Why did I throw this marker? Let's talk about Zeno's paradox. This thing is 2,500 years old. Here comes this philosopher Zeno, who says, an archer shoots an arrow into a stationary target. The archer is a perfect shot. He's going to definitely hit the bullseye. This is what Zeno is wondering. You shoot this arrow to the target. The arrow has to cover this distance. We'll call that distance L, from 0 to L. The arrow is going to cover half of that distance and then have another half to go. Now, when the arrow reaches the half point, there is half to go. So now you take that as a new path, and then there is a half for arrow to cover with half to go. Then you take a look at the remaining path, take that as a new path for the arrow. The arrow is going to cover half of the distance with another half to go. The remaining half. How the hell does it ever hit the target? We know it hits the target. I mean, think about this. You are sitting in those chairs. How did you get to sit in that chair if there is always a half a distance to cover? Right? There is a half a distance point from your car to your chair. And when you accomplish that half, there is half left. And if you take that half as a road, then there is another half right in there. Cover the half, there is half to go. There is always half to go. How do you get ever anywhere? How do you reach the destination? He couldn't figure it out. Couldn't figure it out because the concept that you need to figure that out is formalized in 1800s. Weierstrass gave us the epsilon delta definition of a limit, and today we know to compute the limit, and we see that the distance is 0, which means you're sitting in your chair, the target hit the mark, and you were able to catch that marker, right? Now, you wouldn't move a muscle if you knew that the marker will never reach you because there's always a distance, of whatever distance, there's always half to be covered. But from your previous experiences, you did get hit in the face with various things that people threw, right? So in your 20 years of experience, right, you know that you should duck or catch the object in the way you did. So now, if I look at this, this sits at a quarter mark, this sits at the 8th mark, this sits at the 16th mark. Oh, if I factor out L, isn't this the sequence we had earlier of 1/2, 1/4, 1/8, 1/16? This is the arrow getting 32, arrow getting closer and closer and closer. We know that we get to write an 1/2 to the n. This is our sequence. And here is the limit test. Here is the limit test. Limit as n goes to infinity. All of your n's and k's and i's, whatever variable you get, will all go to infinity in the entire chapter. And the next one. It will never be n goes to 2 or 7. It will always be goes to infinity. We care about the tail end of the sequence. We don't care about the front end of the sequence. You can see the front end of the sequence. You can compute the front end of the sequence, right? You see the arrow covering half and then a little bit more and a little bit more. Right? The question is, how did it hit the target? So now I am taking the limit of this. We have technically 1/infinity. And what is 1/infinity? It is a big fat 0. So what's the distance? The distance from the arrow to the target is 0. Arrow hit the target. You are sitting on the chair because you reached your destination, you reached your target, because in the limit, all of those infinite halfway left, halfway left, halfway left, halfway left, all of those converged down to 0, meaning 0 space left between the arrow and the target, 0 space left between you and the chair, right? You are there. So the limit test is the only test that we use for sequences. The limit test is the only test we say converges to 0. We put C in a circle, at least I do. C in a circle meaning it's a convergent sequence. Do you have divergent sequence? Sure. Infinitely many of them are divergent. Let's take a look at a divergent sequence. Say you have an is equal to simply n plus 1. There you go. What is the limit as n goes to infinity of n plus 1? It is infinity. Because infinity plus 1 is infinity. And that's divergent sequence. So whether it goes to positive or negative infinity, your sequence is, in that case, divergent. So you want to make sure you understand that. Now there are subtleties that will really, break your head as you go along. Subtlety number 1. Convergent or divergent? Right? Well, what you should be asking yourselves first, what the hell is that ordered sequence? I'm expecting numbers to change, right? In something to be ordered so far, we had a half and then a quarter and then an eighth, or we had 1 and 2 and 3 and 5 and 8, right? Now I'm just flip-flopping two numbers. Is there a formula that through swapping ends, 0, 1, 2, 3, 4, 5, will generate this?
-1 to the end.
Excellent, right? -1 to the end. And in this case, you have to start at 0. So when you look at this sequence, -1 to the n, where n starts at 0 and goes on forever. Let's try it. What's -1 to the 0? Positive 1. What's -1 raised to the 1? -1. -1 squared? Positive 1, right? So it seems that this is a sequence because we are able to write a formula where we are able to organize these numbers by n, set of natural counting numbers. Perfect. Now the question is, what's happening with the limit? As you send n to infinity, does it converge or diverge? And the answer is obvious. Yeah. You say convergence. I'm just going to keep my poker face. Let's see if anyone else is going to go for the other one, and then maybe we can have a discussion, rather than me just telling you what and why and be done. For something to converge, it has to fall into one and one number only. So you're thinking about this flip-flopping sequence as you have infinitely many of these numbers in the sequence. Does it converge to a single number or diverges? Now, you're probably thinking to infinity. It definitely doesn't diverge to infinity. Why? Just tell it. Don't use common sense. No, yes.
It diverges because -1 to infinity is -1.
Yes, it's two numbers at the same time. Remember the absolute value of x is not differentiable at 0? Because at that peak, for the absolute value, you have one side of the equation with a slope of +1, the other side of the equation with a slope of -1, and they meet at the same point. And that point cannot have two competing slopes. You can't have slope of -1 and +1. So we say absolute value of x is not differentiable at 0. And the reason is you can't have +1 and -1 at the same time to be the derivative. Same reasoning here. You have sequence of ones. Every other number is 1. That leads into number 1 as you go to infinity. You have what we call a subsequence. You have a subsequence of -1s, which leads into a -1. So at infinity, you have the competition between a -1 and +1. Right? And that's the reason why it diverges. It doesn't, one is not going to balance the other. They're not going to agree to, let's just call it 0 and be done, right? And as much as we, employed our brains right now to think of that, you know what we're going to do tomorrow? We're going to add this. That series. So every comma becomes a plus. And then I'm going to ask you, what's the sum of this? Sleep on that tonight, right? Now, tomorrow we actually have to first finish this section because there are a lot of different definitions. The decreasing, increasing, non-decreasing, non-increasing, monotonic, bounded. This sequence is divergent, but it's bounded. Right? It's bounded because it never dips below -1, so bounded by -1 from below, and it never goes higher than 1, so bounded on top, also bounded by 1. So it's bounded, but it's not convergent, right? It's not convergent because, and then we have monotonic, we have a whole bunch of these things, and then theorem that say bounded monotonic sequences must converge and so on. So we'll deal with those subtleties tomorrow. I'm hoping that you guys will play a little bit with these sequences and think about this stuff a little bit. Don't just disregard this as stuff is not on a test, I'll deal with it later. That's that stuff. This is the stuff that people don't appreciate in Calc 2, this chapter 10. So don't fall off the truck tonight, right? Work on this as if you are having a test next week on this, because it's important. And we'll do the second half of this lecture tomorrow. We'll also do 10.3, and then we're going to stop. We'll continue 10.4 right after the exam. So Thursday is the review and the lab and all of the good stuff. Okay? Bye.
Could you post the Chapter 8 notes and Chapter 9 notes in the Google Docs?